Aloha, my name is Alex Yu. I am a professor of data science and artificial intelligence in Hawaii. In this presentation, I would like to discuss how high-performance computing, massive parallelism, and vector processing power AI in the cloud. Have you ever wondered how a chatbot can generate a sophisticated, human-like answer in less than a second? Or why data centers now consume as much electricity as entire cities? Behind these feats lies the world of high-performance computing, HPC, a realm where scientists, engineers, and even AI researchers harness unprecedented computational power. Just as jet engines transformed air travel from slow propeller planes into supersonic journeys, HPC has turned traditional computing into a platform capable of simulating the universe, decoding the human genome, and powering artificial intelligence systems like ChatGPT. To understand how this is possible, we need to explore three key ideas: high-performance computing as the grand vision, parallel processing as the scaling strategy, and vector processing as the micro-level engine that drives it all. High-performance computing, HPC, is the umbrella term for using advanced computational resources to solve problems that are simply too large, complex, or time-sensitive for conventional systems. If a personal laptop is like a bicycle, fast enough for short errands, then HPC is the equivalent of a rocket, designed for missions that demand extraordinary power. Traditionally, HPC has fueled breakthroughs in weather prediction, nuclear simulations, and aerospace design, tasks where trillions of calculations must be completed in hours rather than years. What makes HPC distinctive is not a single piece of hardware or software, but its goal: to bring together architectures and algorithms that achieve exponential gains in speed and scale. The performance of HPC systems is determined by three crucial factors. The first one is compute speed, formally measured in flops, floating point operations per second. Modern supercomputers operate in the petaflops and exaflops range. The second one is memory capacity. The last factor is input-output speed, which means how fast data can be moved into and out of the system. HPC systems are typically housed in supercomputers, vast networks of interconnected nodes, individual computers, specialized high-speed networks that allow for extremely fast communication between nodes, and massive, high-speed storage systems. The network is often as important as the processors themselves, as data must be moved and synchronized quickly. Within HPC, massive parallelism is the foundational strategy for scaling computing power outward to tackle enormous problems. Imagine a construction project. One worker building a house alone would take decades, but a team of hundreds, each handling a specific part, could finish in weeks. Parallelism applies this principle to computing. Instead of one processor working sequentially, thousands of processors divide the job, crunching numbers simultaneously. Modern supercomputers, such as El Capitan at Livermore Computing Complex, are built on this model of distributed computing, linking countless nodes, individual computers, to act as a single machine. For artificial intelligence, parallelism is indispensable. Training a large language model requires distributing both data and model components across thousands of GPUs. These processors work in concert like a symphony orchestra, where each musician plays their part to produce a unified, time-sensitive output. Vector processing, by contrast to parallelism, works inward at the micro-architectural level. If massive parallelism is about deploying more workers, vector processing is about giving each worker power tools instead of hand tools. In conventional computing, instructions are carried out one piece of data at a time, scalar processing. Vector processors change the rules by applying a single instruction to entire arrays, vectors, of data simultaneously. This technique, historically the core innovation in early supercomputers like those from Cray, is also known as single instruction, multiple data, SIMD. This SIMD capability is precisely why GPUs dominate AI workloads. Their thousands of tiny cores are architecturally designed to perform vector and matrix operations at lightning speed. For example, a deep neural network's forward pass involves colossal matrix multiplications, tasks that vector processors handle in one sweeping motion instead of plotting element by element. Even everyday CPUs now carry vector instruction sets like Advanced Vector Extensions, AVX, on Intel and AMD or Neon on ARM, silently accelerating common tasks like video rendering, image recognition, or physics simulations. These techniques converge most clearly in the cloud computing era. Cloud providers such as AWS, Microsoft Azure, and Google Cloud offer HPC capabilities that once required owning multi-million-dollar supercomputers. With a few clicks, researchers can rent vast clusters of parallel processors equipped with GPUs or TPUs, scaling resources up and down like adjusting the water pressure in a faucet. This democratization has transformed AI. OpenAI's GPT, for example, was trained on a cloud-based supercomputer consisting of tens of thousands of GPUs, each leveraging vector operations internally, coordinated through massive parallel processing strategies, and delivered to users via HPC frameworks at the infrastructure level. Similarly, in genomics, cloud-based HPC enables sequencing analysis that once took months to be performed in days, accelerating precision medicine. Understanding HPC, MP, and vector processing as layers in a hierarchy clarifies their relationship. HPC provides the vision and the infrastructure, the why and where. MP delivers the scaling mechanism, the how at the system level. Vector processing supplies the mathematical horsepower, the how at the chip level. Together, they form the invisible foundation of modern AI and cloud services, enabling society to process knowledge, simulate worlds, and even converse with machines as if they were human. Without this triad, our current wave of AI breakthroughs would remain science fiction. In 1969, humans landed on the moon using computers less powerful than a modern wristwatch. Today, our computing power surpasses those primitive systems by astronomical factors, fueling discoveries that would have seemed unimaginable just decades ago. But this raises questions worth pondering. Are we approaching a plateau in computational growth, constrained by physical limits like energy consumption and heat? Or will innovations in quantum computing, neuromorphic chips, and ever smarter algorithms propel us into yet another exponential leap? For future researchers, these are not abstract speculations. They are the frontiers you may one day help define. So, what do you think? I'd love to hear your perspectives. Please share your thoughts in the comments. If you found this discussion thought-provoking, consider liking, sharing, and subscribing to keep the conversation going. Mahalo.